No.
Yes,
It's simple math. It doesn't make any sense to switch.
I shuffle a deck of cards. Then I deal one card. What is the probability that this card is king? 1 by 13, right? There are 4 cards in 52 cards which are kings. Now I deal another card. What is the probability that the second card is king? Same, 1 by 13, right? Or 4 by 52. What is the probability third card, fourth card, or for that matter, what is the probability that any card randomly picked from the deck is king? 1 by 13.
Shuffling and dealing cards is same as arranging all 52 cards in a sequence, right? And asking the probability that first card is king is same as asking, if I keep on shuffling and dealing cards again and again, n times let us say, and first card is king n1 times among those, probability first card is king is limit n tends to infinity n1 upon n. This is pretty much by definition, right? Similarly, limit n tends to infinity n2 upon n will be probability that second card is king, and so on, where n2 is the number of times second card was king. In the n times the cards were shuffled. Limit n tends to infinity of n1 upon n, n2 upon n, and so on are all equal. Let us say they are equal to p. This combined with sum of n1, n2, n3 till n52 is 4n gives us probability p as 4 by 52 or 1 by 13. Now since we will be using those limits again, it's easier to refer to those limits as probabilities. Probability that that card is king. So main takeaway here is that sum of probabilities will be 4. And whenever cards are shuffled, probabilities of shuffled cards will become equal. Moving on to another random experiment.
Now shuffle the deck again. First card I open. It's 2 of hearts. What is the probability that the second card is king? It's not 4 by 52, right? Now 4 kings are there in these 51 cards. So the probability of second card being king is 4 by 51, slightly more than 4 by 52 or 1 by 13. What is the probability that the third card is king? Same as the second card, 4 by 51. In fact, now, any random card picked from the deck has probability 4 by 51 of being a king.
Let us again consider our n sequences or shuffled cards. To model this, let us consider m of these sequences in which first card is not king. As n tends to infinity, this m also tends to infinity. In fact, m upon n actually approaches 12 by 13, but our focus is not that. If m1, m2, m3 are number of kings in first, second, third columns, or so on, clearly m1 is 0, because first card we're considering came out to be, it's just so happened that first card was not king. And sum of rest of m2, m3, m4, sum of all these should be 4m. Since cards are well shuffled, as m increases, m2, m3, m4 all will become roughly equal. Doing similar calculations as before will give P2, P3, P4 all probabilities equal to 4 by 51. Now, it doesn't matter which card is opened randomly. If it's the second card, third card, or fourth card, whichever card is opened randomly, we can similarly conclude that the probability any other card is king is 4 by 51.
I shuffle the deck. First card I deal. Second card I open. It comes out to be 2 of hearts. Third card I deal. What is the probability that the first card is king? 4 by 51, right? See, the first card, third card, and any other card again have equal probability of being a king, since the second card randomly came out to be a card which is not king. Every other card has probability 4 by 51 of being a king. Now, I shuffle the deck again. If I pick a random card from the deck and it's 2 of hearts, what is the probability that any other random card I pick from the deck is king? Notice that this card, the probability that this card is king is 4 by 51. As long as the first card is opened randomly and it's not king, by randomly opening, that card is found to be not king. I shuffle the deck again. I deal the first card. Now, among the rest of the cards, I look into the rest of the cards and take out 2 of hearts. And since we don't want to know where it came from, and to again randomize the rest of the cards, I shuffle the rest of the deck again. Now I deal the second card. What is the probability that first card is king? When the first card was dealt, it was one of the 52 cards. Probability that first card at that time was 1 by 13. Now, no matter what the first card is, I can always open a random card which is not king, right? And if I deliberately open this card to be not king, then what is the probability that the first card is king? It will remain 1 by 13. Now, what is the probability that the third card, and for that matter, any other card in the deck is king? Now, the probability has slightly increased, right? Because from the rest of the cards, I have removed a non-king card. I can keep on doing that. I can deliberately choose another 2. By just 2, I can choose another card which is not king, and then another, and then another, and then another, and then randomize the rest of the cards so that we don't know what is where, and then I deal a card. Which card has the highest probability of being a king? This card, which I dealt in the beginning, this card, or now this card. If we know that in between I have deliberately opened a card which is not king. If you are playing a game and you will win if you choose a king, which card would you like to choose? Now, as you may feel that the card that comes later has higher and higher probability of being a king, which is actually true. Now let's see how much.
Now this time, before we come to second card, process is same. These are our n total times we arranged all 52 cards in a sequence. N1 times first card was king, and from our calculations, P1 is equal to limit n tends to infinity n1 upon n, which is 4 by 52 or 1 by 13. But we didn't deal the second card randomly this time. We took out a non-king card deliberately from the rest of the cards. So let us suppose in all n total sequences, second card is non-king card we just took out from the deck, while rest of the cards, card number 3 to card number 52, are again random, or we have just shuffled those cards after showing the second card. So P1 is 1 by 13, P2 is 0 obviously, P3 is equal to P4 is equal to so on, P52, let us say all are same, P. Remember, P1 plus P2 plus P3 dot P52 is already 4 from our previous result, which gives us 1 by 13 plus 0 plus 50p as 4. Or P is equal to 4 minus 1 by 13 upon 50, which is 51 upon 13 into 50. Or 51 upon 50 times 1 upon 13. Slightly greater than 1 by 13, right? If we keep on taking out non-king cards from the deck, say second and third, both we have forced to be other than king cards. In that case, the probability comes out to be P is equal to 51 upon 13 into 49, or this time 51 upon 49 into 1 by 13, even larger than the last time. All the while, first card remains unaffected, with P1 is equal to 1 by 13. This looks familiar, doesn't it? It looks like 51 upon 13, the leftover probability after giving 1 by 13 probability to the first card, is being divided into 50, 49, the remaining unknown cards. The total of probability being equal to 4 makes it feel like a physical quantity, as if 4 units of sugar present in 48 units of water to make total of 52 units of solution. This solution, if normally poured into 52 cups of 1 unit, each cup will be 1/13th sweet, right? But if second cup is made to be sugarless after pouring the first cup, sweetness of rest of the solution will increase, while sweetness of first cup or kinginess of the first card remains 1 by 13. It's easy to see why if we randomly open a card and find it to be non-king, the kingness goes equally to every unknown card. Hence, all rest of unknown cards remain equally kingly, so to say. But if I independently open a non-king card from a set of K cards and shuffle the rest of K-1 cards, the card's kingness is redistributed to only those K-1 cards. Rest of the cards remain unaffected.
Now, playing with 52 cards is a little bit too much. So let's take only 3 cards. You win if you choose a king. What is the probability that the first card is king? 1 by 3 this time. 1 by 3 for the second card and 1 by 3 for the third card. Now let us say you choose first card as your card. And from the rest of the 2 cards, I don't know what is what. I open a card which is not king. I deliberately did that, and I always open a card which is not king. Now, what is the probability that this card is king? Notice, if you would have chosen this card, second or third card, I would have opened another card which is not king. Notice that the first card when you chose, the probability before I revealed this card was 1 by 3. And no matter whether it's king or not, I will always open a card which is not king. The probability of this card will remain 1 by 3. Now, what is the probability that this card is king? Notice the rest of the probability of where the king is, the sum of the 3 probabilities has to be 1. This probability can't change. The probability of this card being king is 2 by 3. Now let's close this card and randomize these cards again. Now I arrange these 3 cards and I ask you to choose a card. Let us say you choose first card. Out of the other 2 cards, I open a card randomly and it's not king. Since I opened this card randomly, what is the probability that this card is king or this card is king, provided that what I opened randomly is not king? Notice that now when I have opened the card randomly, the probability of first card being king has also changed. Now there are 2 kings randomly in these 2 positions. The probability of this card and this card of being king is equal. If I offer you to choose between this card or this card, it really won't matter.
Now let's make a weird Monty Hall problem. Let us say there are 5 doors arranged in a circle. There is a car behind one of the doors and the other doors have codes. The procedure is you will be asked to choose one door. After you choose, Monty, the show host, who knows what is behind all the doors, will open one of the doors adjacent to the door you chose and deliberately reveal a goat. Then you will be offered to choose again. What should you choose to maximize your chances? Let's say, following this procedure, you chose door number 2. Monty, who can only touch door number 1 or door number 3, opened door number 3. What are the probabilities of different doors of having cars? You should pause and try it yourself, both by making tree diagram and considering carness of each door. Now initially, all doors are 1/5 car and 4/5 goat, which is another way of saying all doors have 1/5 probability of revealing a car. They remain the same even after you pick door number 2. Each door still has 1/5 probability of revealing a car. But when Monty opens door 3, the carness of door 3 redistributes. It can only redistribute itself between door 1 and door 3. So it goes into door 1. So while the doors you chose, door number 2, and doors 4 and 5 remain 1/5 car, door 3 becomes all goat, obviously, and door 1 becomes 2/5 car, making it the best door. It's important to note that if Monty chooses door number 3 randomly, let us say by flipping a coin to decide between door 1 and door 3, and ends up opening door number 3, which it so happens reveals a goat. Even though the situation looks similar, in this case the carness of all doors except 3 will be equal, and hence equal to 1/4. To see how useful this kingness, sweetness or carness way of approaching problem can be, consider an overly complicated problem. Let's say there are 2 bags. First bag has 3 red, 1 blue ball, and second bag has 2 red and 2 blue balls. 2 balls are randomly taken from first bag and mixed into balls of second bag. Then 2 balls are taken from second bag randomly and mixed into first bag. Then again 2 balls are taken from first bag and mixed with balls of second bag. Now, at last, 1 ball is randomly picked from second bag. What is the probability that this ball is red? Please don't try to solve this, some methods can be really long. Here, we begin with assigning redness to each ball. First bag has 4 balls, each 3/4 red and 1/4 blue. Second bag has 4 balls, each 2/4 red and 2/4 blue. When 2 balls are transferred, redness in first bag is 3/4 times 2. Conserving total redness, rest should be in the second bag, distributed equally among all the 6 balls. So each ball is 2 plus 2 into 3/4 upon 6, which is 7/12 red and rest blue. When we transfer 2 balls back, we can easily see how much redness comes back and gets redistributed equally. So each ball becomes 2 into 7/12 plus 2 into 3/4 upon 4, which is 2/3 red, with a total of 4 balls. Now again we put 2 balls in the second bag and mix, which each ball in second bag 4 into 7/12 plus 2 into 2/3 upon 6, which is 11/8 red. This is redness of each ball in bag 2 now, and probability that a ball drawn at random will be red. At each stage, redness of a ball in a bag is actually probability that the randomly drawn ball is red.